Friends, why we study mathematical induction? We already are familiar with binomial theorem. Binomial theorem states, please look at the slides, states that x plus y raised to power n is equal to nc0 x raised to power n y0 plus nc1 x raised to power n minus 1 by 0 plus ncr x raised to power n minus r y raised to power r and so on plus ncn x raised to power 0 y raised to power n. For example, x plus y square is equal to x square y0 plus 2c1 x raised to power 1 y raised to power 1 plus 2c2 x raised to power 0 y raised to power 2. Similarly, we can extend it further to x plus y raised to power 3 is equal to x cube plus 3c1 x raised to power 2 y raised to power 1 plus 3c2 x raised to power 1 y raised to power 2 plus 3c3 x raised to power 0 y raised to power 3. Friends, the binomial theorem states infinitely many such statements. We must be very clear before we go into the studies of mathematical induction what it is about. That is, actually binomial theorem is not a single statement. It is infinitely many statements. For each n, we get x plus y raised to power n is equal to so on, which was given in the slides. For each of these statements, we are required to prove each one of these. For example, we are required separately to prove x plus y square is equal to so. This is one statement we should prove. Then x plus y raised to power 3 is equal to so and on. This is another independent statement which we must prove. Similarly, x plus y raised to power 4 is equal to so on. And that also should be proved independently. And it continues. Even if you prove for 1000 or 1 million, still there is no end. That is, the number of such statements is infinitely many. How to prove all such statements? It is impossible for any human being or all the humanity taken together to prove all these statements explicitly one by one. So what is the way out? The way out is our friend principle of mathematical induction. It says that you have not to prove, you are not required to prove all the statements explicitly one by one. Rather, you follow 3 or 4 steps which will enumerate and describe a little while later. Similarly, there is another statement. Sn, the sum of first n natural numbers, is equal to n into n plus 1 by 2. Again, friends, I tell you that this is not a single statement. This is a collection of infinitely many statements. The first statement says the sum of first one natural number is 1. The sum of the first two natural numbers is equal to 2 into 2 plus 1 by 2. The sum of the first three natural numbers is 3 into 3 plus 1 by 2. The sum of the first r natural numbers is equal to r into r plus 1 by 2. What I want to emphasize and impress upon you is this, that Sn is equal to n into n plus 1 by 2 is not a single statement but a representative of infinitely many statements. And as there was problem in the case of binomial theorem, similar is the problem here in the case of Sn is equal to n into n plus 1 by 2. That is, no human being or the whole humanity taken together cannot prove all these statements explicitly one by one. And as I mentioned, in all such cases, our friend principle of mathematical induction comes to our aid, which says the following 3 things are sufficient in order to prove such infinite collection of statements. Before I go into the details of principle of mathematical induction, I again emphasize that binomial theorem is not a single statement, it is a collection of infinitely many statements. Sn is equal to n into n plus 1 by 2 is not a single statement, but a collection of infinitely many statements, and it is impossible for anyone to prove all these statements explicitly one by one, and this is why we use the principle of mathematical induction, which says you need to implement only the following 3 steps. What are those following 3 steps, please? Principle of mathematical induction says that you are given infinitely many statements Pn, where each statement depends upon n. For example, S1 is equal to 1 into 1 plus 1 by 2 is one statement because it depends upon 1. S3 is equal to 3 into 3 plus 1 by 2. It is called S3 because it depends upon 3. S17 is equal to 17 into 17 plus 1 by 2. It is called S17 because it depends upon 17. So our principle of mathematical induction says that if you have infinite collection of statements in which each statement depends upon one particular natural number, then what is our goal? Our goal is to check whether each one of these statements, P1, the second statement P2, the third statement P3, and so on, are all of these true or not. And what is the method suggested by principle of mathematical induction? Please look at the slides. The slide says that instead of proving all these infinitely many statements one by one, rather you take the following 3 steps, and if these 3 steps are executed properly and correctly, then in that case all these statements P1, P2, P3, etc. are true. That is, just by execution of 3 steps you are able to prove the truth of infinitely many statements. Now what is the first step? First step says that first of all you prove the base case P1 is true. In the case of binomial theorem, what is the base case? X plus y raised to power 1 is equal to x raised to power 1 plus y raised to power 1. You prove it actually. What is in the case of Sn is equal to n into n plus 1 by 2? What is the base case? Replace n by 1, you get S1 is equal to 1 into 1 plus 1 by 2. You have to actually prove it. And friends, you can see very easily that in both of the case the truth is self-evident. For example, S1 is equal to 1 into 1 plus 1 by 2 is equal to 1 into 2 by 2 is 1, and we know, everybody knows, that the sum of the first one natural number is 1. Therefore, the truth in the base case is established. Similarly, in the case of binomial theorem, what binomial theorem says? X plus y raised to power 1 is equal to x raised to power 1 plus 1c0 x raised to power 0 y raised to power 1, which again is equal to x plus y, and we know x plus y raised to power 1 is by definition equal to x plus y, and therefore in both of these cases the base case is established. This is the first condition or step which is required in order that the principle of mathematical induction is applied. The second case is that, now look at the slide please, that you assume that Pk, the kth statement, is true. You assume it, you have not to prove it. That is, in this particular case, for example, in the case of the sum of first natural numbers k, which is denoted by capital Sk, you assume that it is equal to k into k plus 1 by 2. You assume it, you don't prove it. And then the third step says that taking the truth of S1 and the truth of Sk, you establish the truth of k plus 1th statement Pk plus 1. In some of the cases you may be able to do it, in some other cases you may not be able to do it. In case you are not able to do it, then you cannot apply principle of mathematical induction. That is, principle of mathematical induction cannot be used to establish the truth of infinitely many statements which are under consideration, you will have to take resort to some other mechanism in order to prove the truth of those infinitely many statements. However, if we are lucky, the third step of principle of mathematical induction is applicable. That is, with the help of truth of kth statement, which we have assumed, and the truth of S1, the first statement. If we are able to establish the truth of k plus 1th statement, then in that case we are lucky, principle of mathematical induction is applicable, and therefore all S1, S2, S3, Sn go up to infinity are applicable. So friends, in this particular case, the last step requires assuming the truth of P1 or S1 and Sk, you establish Sk plus 1. Now I apply all these in the case of our two examples, one of binomial theorem and the other is sum of first natural numbers. I have already said in the case of sum of n natural numbers that S1 is equal to 1, we have already established. So now in order to apply principle of mathematical induction, I must assume that the sum of the first k natural numbers is obtained by replacing n by k, that is k into k plus 1 by 2. I am assuming it, I emphasize it, I have not proved it. And now with the help of the statement S1, which says that the sum of the first natural number is 1, and the Sk, which says that the sum of the first k natural numbers is k into k plus 1 by 2, I should show that the sum of the first k plus 1 natural numbers is k plus 1 into k plus 2 by 2. And friends, for that what we should do? We should consider what is the sum of first k plus 1 natural numbers. The sum of the first k plus 1 natural numbers is equal to the sum of the first k natural numbers, and that sum is added to k plus 1. Therefore, this can be written as Sk plus 1 can be written as the sum of the first k natural numbers, please look at the slide, and the k plus 1 number. But already by your induction hypothesis, you have already said that the sum of the first k natural numbers is assumed to be k into k plus 1 by 2, and to this sum you add k plus 1, and after simplifications you get the required number, which is equal to k plus 1 into k plus 2 divided by 2. Friends, you see, just by executing these three statements, now I can assume the sum of the first natural number is 1, the sum of the first two natural number is 2 into 3 by 2, the sum of the first 10 natural numbers is 10 into 11 by 2, the sum of the first 132 numbers is 132 into 133 by 2. You can see the economy, the scale of economy is very large. Similarly, you can prove other. Sometimes it happens that some of the results are true not for first few natural numbers, but then these are true for all natural numbers after some fixed number. I take an example. You take the example, there is a general statement n square is greater than equal to 101. Again, friends, I emphasize, it is not a single statement. It is a collection of statements. It says P1, what is the P1? P1 says 1 square is greater than equal to 101, which is false, of course. But P2? P2 is another statement which says 2 square is greater than equal to 101, which is again false. Similarly, P7 says 7 square is greater than equal to 100. Again it is false. Then 10th statement says 10 square is greater than equal to 101. Again it is false. But when we come to P11, P11 says that 11 square is greater than equal to 101, and it is true. What I wanted to emphasize, Pn, the statement which says n square is greater than equal to 101 for all n greater than equal to 11 is not a single statement, it is a collection of infinitely many statements. What is the special in this particular example is that here the first instance of this general statement is not true. Even the 10th instance of this general statement is not true. However, the 11th is true. So how? But our principle of mathematical induction so far stated insists that we must show first P1 is true and then something else. No, that is not essential. We can modify. There is a generalized principle of mathematical induction which says that it is not essential that we must prove P1 first. Rather, there may be some natural number n. Even it may not be natural, it may be any integer which may be negative also, in which there is some minimum number, say s, for which it appears to be true. You first establish that, and then again make the same assumption as you did in the previous case, that is, you assume that pk is true, and with the help of the truth of ps and the truth of pk, you establish the truth of pk plus 1. And if you are able to execute these three steps correctly, then you can assume that the statements Pn are true for all n greater than equal to s now, not greater than equal to 1 now. You look at the slides. Our goal is to show n square is greater than equal to 1 for all n greater than equal to 11. Now for this, what we should do? We should first of all prove that 11 square is greater than equal to 101, which is true. And we also know that the square of any number greater than 11 square is greater than the 11 square, and because 11 square is greater than equal to 101, therefore the square of any natural number greater than 11 also must be greater than equal to 101. This is the property of transitivity of numbers. And by that we have established that Pn, which says that the n square is greater than equal to 101 for all n greater than equal to 101, is established. The point to be emphasized here is that we did not start from number 1, but rather number 11. There is another example in which we have again a collection of statements which says that Qn is less than 0, is greater than equal to 0 and less than equal to 1. There is a number 1 over n minus 10 and n minus 11. Please look at the slides, please. Now friends, here you can see that for n is equal to 2, n is equal to 10, the denominator becomes 0 and therefore the number is not defined. Similarly, in the case of, please continue looking at the slide. Similarly, in the case of n is equal to 11, we can see that when n is replaced by 11, again the denominator becomes 0 and hence the number is not defined. So in this particular case, again we cannot start our induction process by for all natural numbers less than 12. So in this particular case, we will try to prove the result that 1 over n minus 10 into n minus 11, 1 by of this is less than 1 and greater than 0 for all n greater than equal to 12. Friends, it can be very easily seen. But my emphasis is that in all these cases, the proper sequence of steps must be followed. Otherwise, as I will show later, it may lead to wrong conclusions, incorrect conclusions. So that is very important to be seen. Now I will show. This is already established. Continue looking at the slides. So here we are able to establish that the given number 1 over n minus 10 into n minus 11 lies between 0 and 1. It can be seen very easily. Now another example of application of GPM. Please look at the slides. Here I want to take a more complicated example. Here we have again infinitely many statements Qn, which says 10 raised to the power n plus 4 plus 3 into n 4 raised to the power n plus 6 plus 5 is divisible by 9. Friends, obviously the statement doesn't appear to be that simple. But again I want to emphasize, it is not a single statement. It is infinite collection of statements and here we want to show that the results are not only true for some natural number, these are true for even negative numbers. That is, this statement that 9 divides 10 raised to power n plus 4 plus 3 multiplied by 4 raised to power n plus 6 plus 5 is not only true for 0, 1, 2, etc., but it is also true for minus 3, minus 2, minus 1. But again, whatever discussion we have done so far, that may not be helpful to us, because so far we have restricted to the base case to be a natural number. No, that restriction is also not there. As I mentioned earlier also, that your base case may be a negative number also. So here, as we feel that this case q minus 3, which says 10 raised to power minus 3 plus 4 plus 3 into 4 raised to power minus 3 plus 6 plus 5 is divisible by 9, it appears to us. We'll establish it actually. Once we establish q minus 3, that is the statement for by replacing n by minus 3, then we assume it for k and prove for k plus 1, then it will be proved for all numbers n which is equal to minus 3, minus 2, minus 1, 0, 1, 2, 3, go up to infinity. So the only difference is that in this particular case, we'll take the base case as n is equal to minus 3. Let us take the base case. Now base case, when this n is replaced by minus 3, you can see the statement becomes 10 raised to power minus 3 plus 4, which means 10 raised to power 1 plus 3 into minus 3 plus 6, which is 4 raised to power 3 plus 5, which number ultimately when computed from the slide it is there, it comes out to 207. And because friends, the sum of the digits of the number 207 is equal to 9, and any number the sum of whose digits is divisible by 9 is also divisible by 9, therefore the number 207 is divisible by 9, and therefore the statement q minus 3, which claimed that 10 raised to power n plus 4 plus 3 multiplied by 4 n plus 6 plus 5, when n is replaced by minus 3 is divisible by 9, is established. Now what is the next thing we have to do? We assume by the induction hypothesis that now we assume for any k greater than or equal to minus 3, the result is assumed to be true. I emphasize the word assumed to be true. We don't show it. It is called induction hypothesis. It is an assumption. So in this particular case, we assume whenever k is greater than or equal to minus 3, then 10 raised to power k plus 4 plus 3 multiplied by 4 raised to power k plus 6 plus 5 is divisible by 9. And what is the induction step? The induction step says that assuming q minus 3, assuming qk, now you prove qk plus 1. What is qk plus 1? Qk plus 1 is obtained by replacing every k in the current slide by k plus 1. Whatever is the number obtained, that should be divisible by 9, that we have actually to establish with the help of this current assumption which is on the slide, and the assumption that minus whatever is the number obtained by replacing n by minus 3 is also divisible by 9. With these two assumptions, we try to prove the number which is obtained by replacing n by k plus 1 is divisible by 9. So what is the number, friends? The number which is obtained by replacing n by k plus 1 is on the slide, which says 10 raised to power k plus 1 plus 4 plus 3 multiplied by 4 raised to power k plus 1 plus 6 plus 5 is divisible by 9. This we have to establish. We don't assume it. But what we will assume? We will assume that whatever is obtained by replacing n by k is 2, whatever is obtained by replacing n by minus 3 has already been established. Using these two facts, we will show the current number is divisible by 9. And friends, by proper substitutions etc., ultimately and rearrangement of numbers, because because one power has gone in the power of 10, that power is taken out. So 10 multiplied by 10 raised to the power k plus 1. Similarly, the power of 4 has gone 1, so the 4 is taken out, and rest of the shapes are similar. And then this 10 is written as 1 plus 9. Similarly, 4 is written as 1 plus 3, and this replacement or writing of 10 as 1 plus 9 and writing of 4 as 1 plus 3 is very obvious in the sense that our goal is ultimately to find out factors of 9, because if we have the factors of 9 available in each of the terms, then whole number will be ultimately divisible by 9. And by rearrangement we can see that this is equal to the old number which is obtained by n is equal to k plus 9 multiplied by another number plus 9 multiplied by another number. So you can see by induction hypothesis the first part within the brackets is divisible by 9 and all other terms contain 9 as a factor. Therefore this number also must be divisible by 9, and that establishes that all the numbers of the form 10 raised to the power k plus 4 plus 3 dot 4 raised to the power k plus 6 plus 5 are divisible by 9. We have established with the help of principle of mathematical inductions. Friends, so far I have shown the positive cases. The positive cases are those cases in which we have correctly applied the principle of mathematical induction, and principle of mathematical induction is applicable also. Now there may be situations in which either the principle of mathematical induction is not applicable, or there is a situation that we appear to be following the steps of principle of mathematical inductions correct. We appear to be. However, somewhere there is some flaw in the application, and ultimately we derive some conclusion which is actually faulty. There are various reasons. One reason is that out of the 3 steps, one of the steps is unwittingly, unknowingly missed, and we apply the rest of the steps and we come to a conclusion, but because one of the steps is not taken properly, therefore the conclusion which is derived may or may not be correct. We should take care. Secondly, sometimes we take all the steps, however, while application of the step, some logical step is overlooked, and because of the overlooking of the some logical mistake is committed, and ultimately we feel we have applied all the steps of principle of mathematical induction, still we are not getting the correct result. It cannot happen. It is our feeling. So now I'll explain 1 or 2 examples in which I'll show that either a step is missed or some logically incorrect step is taken. In both of these cases, a conclusion is drawn which is neither true nor intuitively correct. We take one of the cases like this one. Please look at the slides. The slide says that 2 plus 4 plus 2n, that is the sum of the even numbers up to 2n, is equal to n minus 1 into n plus 2. Friends, you can see this is a wrong statement, because some of the one natural numbers, when n is 1, then you will be getting it is 0, which is not true. Similarly, you can take n is equal to 2, you will be getting 2 plus 4. 2 plus 4 should be 6, but on the other side, if you take 2 minus 1 into 2 plus 2 minus 1 is 1 and 2 plus 2 is 4, that is 6 is equal to 4. Again it is wrong. Similarly, you take n is equal to 3. You will see 2 plus 4 plus 6, which comes out to be 12. But the right hand side says 3 minus 1 is 2 and 3 plus 2 is 5. So it is 10, which is again wrong. But we will show. Of course, we will be doing some error, but we will show that sometimes we may follow some of the steps, lead to a conclusion like this, which is wrong, and then we will explain why it has been wrong. So in this particular case, We say all these statements as theta k is equal to 2 plus 4 plus 2k is equal to k into k plus 1, 2 is equal to k minus 1 into k plus 2. Now we try to prove that it is true. Please continue looking at the slide. Here we assume that theta k is true, and with the help of that we prove theta k plus 1. You can see theta k plus 1 is the sum of the first k plus 1 even numbers, which can be written as 2 plus 4 plus 2k, this whole added to 2 into k plus 1. And after simplification we get k into k plus 3, which tallies with n minus 1 into n plus 2. That is, sum of the first n even numbers is equal to n minus 1 into n plus 2. If in this we replace n by k plus 1, we get this statement. This means by assuming the truth of the statement for first k even natural numbers, we are able to establish the truth of the statement for first k plus 1 even natural numbers. But as I mentioned earlier and as I again show here on the slide, please look at it. If the result is true, then 2 will be equal to 0, 6 will be equal to 4, and 12 will be equal to 10, which is wrong. So what has happened? What is wrong with the proof which we have given? The problem with the proof is that we didn't establish the base case when n is equal to 1. We did not establish. That is also required to be established in order for the proper application of principle of mathematical induction. And you can see, if we look back the slides 2 steps back, where we have said 2 plus 4 plus 2n is equal to n minus 1 into n plus 2. For n is equal to 1, it reduces to 2 is equal to 1 minus 1 into 1 plus 2 is equal to 0, 2 is equal to 0. This step has to be established. We didn't bother to establish it. And because it is wrong, therefore we cannot go ahead with our application of principle of mathematical induction. I want to emphasize through this is that each step is very important, though it may be quite trivial. Until unless you apply each of the step in sequence, proper sequence, it may lead to a wrong result. We'll take another take a look at another example where also there is some logical fallacy and still the result is derived correctly, though it is not correct otherwise. So please look at the slides further. Yeah, here we want to see, please look at the slide. We want to show that if there is a group of persons having n persons, n may be 100, maybe 1000, maybe any number, we by some incorrect reasoning or an application of principle of mathematical induction may be having a tendency to prove the age of all the person in the group, maybe of 1000 persons, is same. That is, if there are 100 persons, P1, P2, P3, including father and son, including mother and daughter, including other relatives and all that, they are say 100 in number. We'll show by a following reasoning that the age of all the persons in this group is same, say 25 years. How it follows? We say, as our principle of mathematical induction requires, first you prove the base case n is equal to 1. Now, it is very clear that if there is a group of just one person, then the age of all the persons in the group which consists of a single person is the same. There is nothing wrong in it. So the base case that if a group has just a single person, then the age of all the persons in that group is equal, is completely correct. Now we assume, because our principle of mathematical induction says that you can assume that a group of k persons have same age. So P1, P2, P3, Pk may be a group of persons which is k in number. By induction hypothesis, all these persons have same age. There is nothing wrong with this assumption. It is allowed by principle of mathematical induction. Now we have to show that from these two facts, that the age of all the persons in a group of one person only is same, and the age of all the persons in a group of k persons is also same. We have to show the age of all the people in a group. You may not look at the slide anymore. In a group of k plus 1 persons should be same. In order to show the age of all the persons in a group of k plus 1 persons same, we are allowed to make use of two statements. Number one, the number of persons in a group, if it is 1, then the age are equal of all the persons, and if in a group the number of persons is k, then the age of all these persons is k plus 1. Now friends, look at the slide. The k plus 1, you should look at the slide now. The group of k plus 1 persons can be divided into two groups. One group consists of P1, P2, Pk, and the other group consists of P2, P3, Pk plus 1. Because the second group starts with the second person and ends in k plus 1th person, therefore the number of people in the second group is also k. And in the first group, P1, P2, Pk, the number of persons is again k. And our induction hypothesis allows us to assume that whenever the group has k persons, then the age of all the persons in the group is same. So friends, this means the group of persons P1, P2, Pk must have the same age. Similarly, the persons P2, P3, Pk plus 1, because their number is again k, therefore they must also have the same age. However, P2 is common in 2. The age of P1, P2, P3, P4, Pk is equal to the age of P2. And in the second group, the age of P2, P3, P4 and Pk plus 1 is equal to again the age of P2. This means the age of all the k plus 1 persons must be equal. But it is counterintuitive. We have never seen that whenever there is a group of more than one person, arbitrary persons, father and son, mother and daughter, and all other combinations of people are there, and still their age may be same. No, it is not possible. But we have concluded it just now by application of principle of mathematical induction. So either the principle of mathematical induction is not justified, or there is some flaw in our reasoning. Friends, actually there is a flaw in our reasoning. Actually, while applying the induction step, we have assumed Pk plus 1 greater than equal to 3. Only because of this, we are able to include P2 in both of the cases. However, our k plus 1 may be equal to just 2. And if our k plus 1 is equal to 2, then our k plus 1 members are equal to P1 and P2. And if we and in this particular case, k is equal to 1. And if I divide this set of k plus 1 members into two subsets, each of k elements, then one set will be P1 only, the other set will be P2 only. And from here we cannot conclude the age of P1 is equal to age of P2, because P2 is not common. So friends, what I want to emphasize, sometimes we even apply the principle of all the steps of principle of mathematical induction, but somewhere there is some logical flaw. As in this particular case, we assumed k plus 1 is greater than equal to 3. Such sort of subtle mistakes which are not so evident may lead to wrong conclusions. We must be very careful while applying the principle of mathematical induction in proving the validity of infinitely many statements. So, I hope this is clear to all of us what was the fallacy. Friends, principle of mathematical induction so far applied by us. You may not look at the slide for some next 5 minutes or so. The principle of mathematical induction so far, which we have applied, started already with some formulae or equations. We said that the sum of the first n natural numbers is equal to n into n plus 1 by 2. Similarly, we started with the binomial equation and so on and so forth. This is not the only application of, rather it is very trivial application of principle of mathematical induction. What is the actual application of principle of mathematical induction is that from the various examples we study, there are patterns in numbers and so many equations occur among them. Through the patterns, on intuitive basis, we feel that this should happen. So the first step, through intuitive induction, we find some patterns. Rather, the patterns are not given to us as were given in the case of 1 plus 2, 3 plus 3 plus 4 plus n is equal to n into n plus 1 by 2, or binomial theorem x plus y raised to power n is equal to so on and so forth. No, we are not given all these. Rather, we find the patterns. From the patterns we feel that this should happen, and once we feel that this should happen, then we apply principle of mathematical induction in order to verify that whatever we feel intuitively is actually true or not. I take an example. Please look at the slides. The slide has, please look at the slides. The slide has an example. Please look at the slides. It is very important for me to make you look at the slides. Hello. There is a call. Yeah. Please. Yes.
Hello?
Yeah, hello.
Hello?
Yes, please.
I just want to know what's the difference between
yes,
this conjective normal form and principal conjective normal form.
Again, repeat it, please.
Thank you, sir. So my name is Ajaz. I am from Srinagar.
Yeah. Again, repeat your question, please.
What is difference between conjective normal form and principal conjective normal form?
Please, we will come to that subject later on. We are talking of principle of mathematical induction. And
okay, thank you, sir.
In order to answer this question, I must use a slide on which your answer should be given clearly. Please ask the question relevant to your the topic today, and you may send through email your question. You will be immediately getting today itself. After 5, when this lecture is over, you send the email, you will be getting the response to this by 5:30 or so. Thank you, please. So now I will again carry on further. Thank you for asking the question, of course. You see the pattern. I was saying, after seeing a pattern, we feel something should happen. And when something happens, we devise a formula. And then we actually apply the principle of mathematical induction to check whether whatever we have intuitively judged is true or not. Now here it is a sequence given on the slide. 13, 23, 33, 43, 53, 63, 73, 83, 93. Friends, out of this, those numbers like 33, 63, 93, in which the second digit is a multiple of 3, they are of course not prime. That is, 33 is not prime because it is a multiple of 3, 63 is not a prime because it is a multiple of 3, 93 is not a prime because it is a multiple of 3. But rest of the numbers from our past experience or otherwise we can prove, like 13, 23, 43, 53, 73, 83, all are primes. So it may give an idea to us to say that any number of the form 10k plus 3, where k is not a multiple of 3, may be a prime number. Now, this is our intuition. So the statement, there are infinitely many statements Pk are the statements. Pk says 10 multiplied by k plus 3 is a prime number provided 3 does not divide k. We have infinitely many such statements. Now, this is our feeling, it is intuition, but we know intuition, you may not look at the slide anymore for the time being. So, but many times intuition leads us astray. We know a subset of a finite set always has lesser numbers, but in the case of infinite sets, a subset have as many numbers as the main or parent set. So our intuition goes wrong in many of the cases. So here the intuition says that 10 multiplied by k plus 3 is a prime number if k is not divisible by 3. So now we cannot depend upon our intuition. So we try to apply the principle of mathematical induction in order to establish the truth of this one. Is it okay or not? So now we try to establish the truth of this one. Now the very first case, that is when k is equal to 1 or n is equal to 1, because 1 is not a multiple of 3, and 10n plus 3 or 10k plus 3 when n or k is equal to 1 is 13, and we know from our experience and otherwise also it can be proved that it is a prime number. So the base case is established. Now we come to the next, that is we assume 10k plus 3 is prime number. It is an assumption, you are allowed to assume this, but with the help of these two, that is step 1 base case and this assumption, you are required to establish that 10 multiplied by k plus 1 plus 3 is also a prime. So let us consider the cases. Now k, because it is not divisible by 3, so either it may be of the form 3s plus 2 or it is of the form 3s plus 1, that is on division by 3 either the remainder is 1 or the remainder is 2. So first of all we take the case 3s plus 2, that is k is equal to 3s plus 2 and 10k plus 3 is a prime number. You need not look at the slide for the time being. So friends, your k is equal to 3s plus 2, that is on division by 3, the remainder is 2, therefore k is equal to 3s plus 2. What will be k plus 1? K plus 1 will be equal to 3s plus 3. But 3s plus 3 is divisible by 3, that is k plus 1 is a number which is divisible by 3. What does this mean? This means that because already we have said that all those numbers for which n is divisible by 3 are to be excluded, that is the truth is vacuously there, that is we are not going to establish the primality of 10n plus 3 if n is a multiple of 3. So in this case, when your k is equal to 3s plus 2, k plus 1 becomes 3s plus 3, which is divisible by 3, and hence we will not be taking into consideration the primality of k plus 1, because it is not going to be by our own statement that only numbers of the form 10k plus 1, 3, where k is not divisible by 3, are to be considered as prime. Now we come to the second case, when k is equal to 3s plus 1. So what will be the shape of k plus 1? Look at the slide please. K plus 1 is equal to 3s plus 2. So here the verification is required, because 3s plus 2 is not of the form which is divisible by 3. So friends, 10 into k plus 1 plus 3 is equal to 10k plus 3 plus 10. And it is given 10k plus 3 is prime. But can from the primality of 10k plus 3, we can show that 10k plus 1 plus 3, which is equal to 10k plus 3 plus 10 is prime? No. There are so many examples. I give you an example here, that is, in this particular case, if you take 10 into 19 plus 3, which is 193, which is prime. But if you add 10 to this, we get 207, which is not a prime number, because it is divisible by 9. So what I mean to say, while applying principle of mathematical induction, we came to a stage where, assuming 10k plus 3 is prime, we are required to show 10k plus 3 plus 10 is also prime, which is not possible. So what I want to convey through this is that sometimes you go ahead with the various steps of principle of mathematical induction, you may get stuck at some stage, and if you don't have any bypass, in that case principle of mathematical induction cannot help you in proving the infinitely many statements which are required to be proved, and hence you have to give up at some stage, and you will have to adopt some other mechanism of establishing the truth of infinitely many statements which are before you, if they are really true. They may not be true, but even if they are really true, then you have to adopt some other mechanism so that the truth of those statements is established. Okay. Friends, the topic, the block of V2 consists of mathematical induction, relations and functions. In the remaining time, about 3 or 4 minutes. Yes, please. Hello. Please come up. Hello.
हेलो
Yes, please.
मेरा क्वेश्चन है
हाँ जी बोलिए.
हेलो सर
हाँ जी बोलिए.
हेलो
Yes, please. Come up, please.
हेलो एक्चुअल आवाज ही नहीं.
Hello.
हेलो
Yes, please.
हेलो वी आर कॉलिंग फ्रॉम TLC 778.
Yeah, please carry on.
कम ऑन
Please carry on.
एक मिनट सर. Excuse me sir, actually my question is what is Hamiltonian path in graph theory?
Yeah.
Yeah.
Hello. Please come up.
Yes sir.
Yes.
Sir, exactly my
Well,
question is.
well, I advise you, please listen to me, because you are not audible. Therefore, you send your question by email. My email, the voice is not clear. I request you to send your question by email. My email address is lalmanohar@hotmail.com. You send your question by tomorrow morning about 12, you will get the answer back. Hello. I hope.
Thank you, sir.
Okay, please. Thank you very much. So, friends, in view of the paucity of time, we have 2 or 3 more minutes. We have already talked about relations in the previous lectures. In relations, I have told you, the mathematical relation is a sort of, because there is not much time, I cannot go into the fine details of the concept of relation, mathematical relation. However, I may emphasize upon you the concept of mathematical relation is a generalization of our everyday relations. For example, we take the relation of mother. Now suppose y1 is mother of x1, y2 is mother of x2, y3 is mother of x3. We can represent it as a mathematical set of ordered pairs x1 y1, the set consisting of the ordered pairs x1 y1, the second ordered pair is x2 y2, the third ordered pair is x3 y3, and so on, in which x1 is any, xi is any person, and the corresponding yi is the mother of xi. Now you see the set of all these ordered pairs xi, yi such that I is equal to 1 to infinity as long as is the number of persons. You can say this set represents the same information as saying mother of x1 is y1, mother of x2 is y2, mother of x3 is y3, and so on. The same information conveyed by the set of ordered pairs. This was the relation of mother. Similarly, you can consider other human relations. Now we forget where X, I and Y are human beings. We take capital X and capital Y. Instead of set of persons, we assume these are arbitrary sets. Take their cross product. The cross product of X and Y consists of the all ordered pairs small x, small y, where the small x belongs to capital X and small y belongs to capital Y. In this way, we get the cross product. Then the definition of a mathematical relation is something like this, that it consists of any subset of the set of X cross Y. So, this is the generalization of the relations among human beings. I repeat, a mathematical relation from a set X to a set Y is a subset of the cross product X cross Y. Now, this is the definition of a general relation. In mathematics, sometimes we are more interested in relations from X to X itself instead of X to Y, where Y is not equal to X. Because our interest is in relations from a set X to itself, such relations are generally, instead of being called relation from X to X, we call them relation in X. So friends, this is a particular case of binary relations. That is, the relations may not be restricted to only two sets. The relation of between in natural numbers, 3 lies between 2 and 4 is not a binary relation, it is a ternary relation, that is, it requires 3 numbers, 2, 3, 4, where the middle one is in between the two extreme ones. 7, 5, 9 is not true. That is, 5 doesn't lie between 7 and 9. Therefore, it does not belong to the relation of between in natural numbers. What I wanted to emphasize through this is that the relations need not be between just two sets. The relations may involve more than two sets also, as just now I said that there are 3 sets involved in the relation of between. Excuse me. However, our interest is generally in binary relations. I'll come to discuss. There are some special binary relations. Friends, because the topic is very vast of binary relations and other relations, and then functions, etc. I'll be taking this topic in my next lectures. However, if you have any problems, either you may ask just now, or the best course will be, because the audibility was not proper, you send your emails today itself. By tomorrow 12 o'clock, you will be getting answers to all those queries concerning either discrete mathematics or other course. You may send through email. I repeat my email address, all small letters, LALMANOHAR, lalmanohar.hotmail.com, lalmanohar@hotmail.com. I am waiting for your questions, and I hope you must have understood the principle of mathematical induction, its application, the possible flaws in its application, etc. And I hope you must have gained. You should try to do some exercises.